Modern design of telescope eyepieces have revolutionized visual astronomy with breakthroughs in computer optimization and new optical glasses. Today's top eyepiece manufacturers design high-performance eyepieces with superior edge performance with a wide range of apparent fields and long eye relief. So how do you choose? Today there are many premium quality eyepieces to choose from for your telescopes. But with so many focal lengths and a variety of apparent fields of view, how do you choose what's best and what fits you best for your specific telescope? Here are the eyepiece selection considerations. We're going to find out the lowest useful magnification of your telescope, the highest useful magnification, how to choose eyepieces between lowest and highest useful magnification that will give you the medium steps in power with your telescope, selecting a set of eyepieces that have the apparent fields of view that you desire that will produce the true fields of view that you typically require for the objects that you observe. And then you need to consider a set of eyepieces that have enough eye relief so that you can have the eye comfort that you require. This is how a telescope works. Aperture, focal length, F ratio. The telescope focal length divided by the telescope aperture equals F ratio. From here we can determine magnification and true fields of view. So let's discuss focal length. All telescopes and eyepieces have optics polished to focus at a certain distance. This distance between the lens and the focused image, usually measured in millimeters, is called focal length. A longer focal length lens produces a narrower field of view, and a shorter focal length lens produces a wider field of view. So how does magnification work? The focused image from the telescope lens is being magnified by the eyepiece. In this case, the telescope focal length is about 160 millimeters, and the eyepiece is only 20 millimeters, producing 8 times magnification. This is how we calculate magnification. What you do is you take the telescope focal length, usually in millimeters, divided by the eyepiece focal length, also in millimeters, and that will equal magnification. Or you can take the telescope aperture in millimeters and divide it by the exit pupil in millimeters, and that will also equal the magnification. Now we'll discuss exit pupil. Every telescope and eyepiece combination will produce an exit pupil. It's the focus beam of light where the image is viewed. The diameter of the exit pupil changes with magnification. Lower magnifications produce a larger exit pupil, giving a brighter image. Higher magnifications produce a smaller exit pupil with less image brightness. This is the formula for calculating exit pupil. You take the eyepiece focal length in millimeters and you divide it by the telescope F ratio, and that will give you the exit pupil number. Or you can take the telescope aperture in millimeters and divide it by magnification, and this will also give you the exit pupil number. Both of these numbers will end up being in millimeters. Observing faint objects. Telescopes are light-gathering devices capable of focusing images of objects at incredible distances. Under dark skies and the right telescope and eyepiece combination, it's possible to visually observe faint galaxies that are many millions of light years away. Of course, with more light to your eye, you can see the faintest details of every object you look at. But to see the faintest details, you need to be comfortable and observe at the lowest useful magnification. In order to see the faintest and the most distant celestial objects possible through your telescope, you need to find the eyepiece focal length that will produce an exit pupil that will closely match the entrance pupil of your fully dilated eye when dark adapted. For young people, it's not unusual for pupils to dilate to 7 millimeters or more. Older people may have pupils that can only dilate to 5 millimeters. So visit your eye doctor to have your fully dilated pupils accurately measured. With this information, you can choose the perfect lowest power eyepiece. Now, for determining lowest useful magnification power, try to determine which eyepiece on your telescope will produce an exit pupil that comes closest to matching your fully dilated eye. If you select an eyepiece that produces a larger exit pupil than what your eye can dilate to, then you're not able to experience the full brightness of the focused image. It's important to calculate the eyepiece focal length for lowest useful magnification. Here's a useful formula for calculating the eyepiece focal length for lowest useful magnification. What you do is you take the telescope aperture in millimeters and you divide it by the fully dilated eye in millimeters. That will give you lowest useful magnification. Then take the telescope focal length in millimeters and divide it by the lowest useful magnification number. That'll tell you which eyepiece focal length you need. Another typical way to find lowest useful magnification is to use the rule of thumb of 3.5 power per inch of aperture. With a 102 millimeter lens, a 4-inch aperture telescope, the lowest useful magnification is 14 times. But what about high power observing? Telescopes are also detail resolving devices capable of focusing highly detailed images of objects. Under steady skies called good or perfect seeing conditions and the right telescope and eyepiece, it's possible to visually observe incredibly fine features of bright objects like the planets and the moon. But there's a limit to how much magnification you can use, and that limitation will be based on the atmospheric seeing conditions and the telescope's aperture. Having several eyepiece focal lengths from lowest useful magnification to highest useful magnification will maximize your observing potential. Atmospheric seeing and the Pickering scale. The atmosphere can be very turbulent, called bad seeing, to perfectly calm, called perfect seeing. Turbulence in the air causes stars to scintillate or twinkle. Viewing conditions with bad seeing, 1 to 4 on the Pickering scale, distort images of stars, planets, and even the moon. This distortion looks much worse with larger aperture and higher magnification. Viewing conditions with good to perfect seeing, which would be 7 to 10 on the Pickering scale, allows telescopes to be used at higher magnifications, which will reveal fine details on every object you observe. The Pickering scale shows 1 is the worst seeing with 5 arcseconds or more star blur at the sharpest focus, and 10 is perfect with 0.5 arcseconds or less. Average nights of seeing would range from 5 to 7 on the Pickering scale. To determine highest useful magnification on any given telescope, determine the telescope's aperture in millimeters and multiply that number by 3. With this 102 millimeter refractor, the result is 306 power. So how do you calculate the eyepiece focal length for highest useful magnification? So this formula is for calculating the eyepiece focal length for the highest useful magnification. What you do is you take the telescope aperture in millimeters, multiply by 3, and that'll give you the highest useful magnification number. Or a more conservative number could be brought about by taking the telescope aperture in inches, multiplying it by 60, or if your seeing conditions are not that great, maybe by 50, and that would give you the new highest useful magnification number. Then you take the telescope focal length in millimeters and you divide it by the highest useful magnification number. That will give you the eyepiece focal length that you need to get. What's aperture masking and how can it improve your high power observing? During times of poor to bad seeing, images of the moon, planets, and double stars observed at higher power can be improved by reducing the entrance aperture of your telescope. Masks can be made from various sizes from cardboard. With less aperture, there is less resolving power, but images will look sharper. Now that you understand lowest useful magnification and highest useful magnification, you need to calculate the medium steps in power so that you can get the best observing potential possible. Many astronomers own several eyepieces that range from lowest to highest power for their telescope. Medium power eyepieces are also selected by magnification, apparent field of view, and eye relief. Many astronomers begin their observations at low or lowest power and then gradually increase power until the object is best seen. What are eyepiece multipliers? Increasing magnification of your lower power eyepieces can also be done by adding focal extenders or a Barlow lens to your eyepieces. The advantage is that these devices can increase the magnification of all your eyepieces, but the eye relief will remain unaffected. This is especially useful if you need long eye relief of your long focal length eyepiece, but you want more magnification. Many people want to know what's the difference between apparent field of view and true field of view. True field of view is the actual degrees of sky coverage that you're looking at, the chunk of sky that you see. But apparent field of view is the angle of degrees from your eye to the edge of the field stop in the eyepiece. When you're looking through an eyepiece that has wider apparent field of view, you not only get more true field of view, but you get this effect that you're seeing through a wide picture window. More apparent field of view gives you more true field of view. The Orion Nebula M42 is 60 arc minutes by 66 arc minutes in angular size, or twice the size of the full moon in the sky. This is M42 with a telescope of 714 millimeters of focal length and a 68 degree 20 millimeter eyepiece. This gives you 35.7 power, and it will also produce a 1.9 degree true field of view. Then in this other image, we've got M42 with a telescope of the same focal length, 714 millimeters, and the same focal length of eyepiece of 20 millimeters. So we're getting the same magnification of 35.7 power. But with 100 degree apparent field of view, we're getting 2.8 degrees true field of view. You actually see more area around the object, but at the same magnification. So how do you calculate true field of view? You take the eyepiece apparent field of view and you divide it by magnification, and that will equal true field of view in degrees. Or another way of doing this is take the eyepiece field stop. You can get that from the manufacturer. You divide it by the telescope focal length in millimeters, and you multiply it by 57.3, and that will also give you the true field of view number in degrees. You have to relax to see more, and this is the importance of eye relief. Eye relief is the distance from the last surface of an eyepiece of which the observer's eye can see the full viewing angle. If the observer's eye is outside of this distance, then the observer will not see the full viewing angle. Long eye relief eyepieces give more eye comfort, and if long enough, 18 millimeters or more, will allow observers to wear glasses when observing. That's usually needed for someone that has astigmatism in their eyes. Generally speaking, short focal length, higher power eyepieces have less eye relief than long focal length, lower power eyepieces. Eye relief distance information is provided by the manufacturer. You love to observe deep sky objects, but what about light pollution? Just because you're not under the best dark sky sight doesn't mean that you can't still observe some bright galaxies, star clusters, and nebula. Improving your skills as an astronomer has a lot to do with how often you observe, even if that means you do most of your observing near city lights. To improve the view of deep sky objects under light-polluted skies, you can use moderate increases in magnification, which will make the background sky look darker. There are also special filters that you can use with your eyepieces that can increase contrast. To judge the quality of your sight, you can use the Bortle scale. You can have the darkest skies possible, but also not see very many stars, and that has to do with atmospheric transparency. The Bortle scale is a 9-level numeric scale that measures the night sky's brightness of a particular location. It quantifies the astronomical observability of celestial objects and the interference caused by light pollution. Class 9 on the Bortle scale is the most light-polluted sky, where you can barely see any stars in the sky at all. When you go all the way down to Class 1, you're now under perfectly dark sky conditions, where the sky's black to the horizon. But there's another aspect that's very important to astronomers, and that is sky transparency and atmospheric extinction. It's possible to be under a dark sky, but not to be able to see many stars due to poor sky transparency or atmospheric extinction. Generally speaking, the very best dark sky sites are far away from city lights, you're up high in elevation with smooth terrain, and the sky has very little water vapor or aerosols in the atmosphere. You can learn more about sky transparency and atmospheric extinction at this website. So to sum it up, by choosing the right eyepieces, you're going to have the most relaxing, most detailed observations you can possibly make. The more comfortable you are and the longer you look, the more you see. Long eye relief eyepieces with large apparent field characteristics allow you to relax more at the eyepiece by letting you back away from the optics while allowing your eye to comfortably scan the field of view in order to use averted vision. A relaxed eye observing at any magnification that's not staring at the object can see fainter details and finer structure than a strained eye. So happy observing.
In terms of robots that go into space, the sampling and caching system on the Mars 2020 mission is the most complicated, most sophisticated thing that we know how to build. This is the system that allows us to take core samples of rocky material on the surface of Mars, carefully seal them in very sterile, clean vessels for eventual return to Earth. We've been working on this sampling and caching system for 7 years, and that's because it's a tough job.
We're testing the equipment to make sure that it's going to work when we get to Mars. It has to function on its own. We have to think of all eventual possibilities and try them here first. And then if they don't work, change it now, because we can't make any changes later.
To drill into the rock on Mars, pull out intact core samples, seal them hermetically, and to be all done autonomously by a robot hanging off the end of a rover on the surface of Mars has been a challenge. We've got actually 3 robots necessary to do the sample and caching system. Our big robotic arm out on the front of the rover, that takes our drill, pushes it against the surface, and allows us to take core samples. Then we put that core sample in the bit carousel, the second robot that takes that from the robot arm and puts it down inside our adaptive caching system. This is the part of the sample and caching system inside the rover. We've got a little tiny robot, a special robot arm called the SHAW, the sample handling arm. It takes the samples out of the bit carousel and moves them through volume assessment, image taking, and eventually to sealing, and then replaces the cylinder containing the sample in a storage spot, all on its own in the matter of a few hours. We have designs on bringing them back in a decade. Mars has been at the fore of our consciousness about the questions of life. Could life exist in one of our nearest neighbors? I think we have a lot to learn, life or no life, about the evolution of our solar system, about our planet, by looking in depth at rocks brought back from Mars.
Well, hello everybody. This is Scott Roberts, and today we're with Gary Palmer from the UK, and of course Jerry Hubble here. And it's a great Friday. I hope you guys enjoyed some of the other programming that we had today with choosing and using eyepieces, and NASA's great videos from the Mars 2020 rover. That sample collection device is pretty amazing. I've watched the video now like 10 times, and it is just staggering the amount of technology that they've got in there to do all of that. It'll be very cool when they bring back real samples from Mars, and that'll allow us to compare against maybe the Martian meteorites that we have here on Earth, to say, oh, yep, those are real. That's the real deal, So
Right.
right.
I'm curious to see how that equipment lasts with all the dust. You can see all that fine equipment with all the robotic arm and all the other stuff underneath there. You got to wonder.
Getting
You got to wonder how the
backwards
dust is going to be.
so.
Yeah.
It's amazing that the rovers have lasted as long as they have up there anyways, I know that they overbuild these things to a degree, but they have to be lightweight. There's so many constraints. It's unbelievable. The last time I was at where I took a tour through the Mars yard and everything at the Jet Propulsion Laboratory, they let me hold some of the parts from the rovers.
Oh, that's cool.
And they're made out. A lot of them are made out of like titanium and stuff. And you would not believe how large some of the parts are and how light they are. So it's pretty interesting. I wish I could have seen the Mars helicopter though. I like drones. I love that stuff. I like flight in general, and so it was just really cool. Gary, we'll get started with you today. You've been taking images of the sun,
Yes.
as you often do. You know, being one of the really top solar imagers around today, and you got the nerve to put your solar scope on an Exos 2 with PMC-Eight. So how did it go?
Yeah, it's been working really, really well. We've had very, very few problems. To be honest, using it on that system, it works quite well with the Explore stars. It's just so simple, and for the light control and moving around,
that's cool.
Very easy to adjust the speeds. So it doesn't really, it's not really worth connecting it all up to a planetarium. Really, as long as you're fairly well pointing.
That's why people are using this for astrophotography.
Right, exactly.
And we keep telling people, no, you know, an Explore Stars really wasn't designed for the astrophotographer. But I think there is some convenience, you know. So
that's the thing, and the speed controls and all of those sorts of things seem to work really well. They're having no real problems, and we're running at quite high magnification into the sun. This is not just full disk images. These are running at f30, f28 to f30. One of the systems we had running last week was running be somewhere around a 7 meter focal length into the sun. Time we got the magnification on there, so no complaints from my side. It's working. It's working really well at the moment.
Well,
That's great. That's good to hear. Yeah.
Great. So, were you able to capture some images?
Yeah, we've had some. Let's run a screen share up.
Okay. All right.
And just share the screen. Start sharing. There we go. And we're actually running through some of the processing from today at the moment. So if I run through these. There wasn't a lot of prominences around today, so we're mainly looking at sunspots and active areas, and these are literally not processed yet. They're just stacked from the raw videos. There's 3 active areas on the sun at the moment. They're just running to some that are slightly better detail. There we go. So that will be in magnesium. That's in magnesium. So we can see parts of the active area here. They were imaged about somewhere around 11 o'clock, 11:30 this morning. And
how many solar astronomers are imaging in magnesium?
There's a few. It's quite rare at the moment. The easiest way that I put it in a talk is that you're contributing to science. There's so really a limited amount of information on this. And last year when I was doing some work, and I did some work on the initial testing with it, we were picking up lots of different detail, lots of structures that you couldn't see in, say, white light or sodium or hydrogen alpha. Because if we look in this shot from this morning in hydrogen alpha, the chromosphere is covering all of the detail that's going on. So while it looks fantastic, and a lot of people equate it to a shag pole carpet, shag carpet, that sort of thing, it does cover a lot of what's going on underneath it. So the actual sunspots that are there, you can see there's a small group here, and there are some small pores over on this side, but they're all hidden by the chromosphere. So using things like magnesium or sodium, or even white light can produce different detail. Probably the easiest way of explaining it is it's very similar to an onion. So if you imagine we get in the skin of an onion and we're peeling off the skin itself, and then we're peeling each layer, that's very similar to how the wavelengths are working on the sun. And the same view here, this is in sodium. So you see less of the active area, but you do see more prominent sunspots and the pores that are going on around it.
Yeah.
If we look back to last week, I think it was the 30th. Let me just switch drives. There we go. And we come down to there's a couple on here. So we had the large prominence. I think I showed this last week, but it hadn't been processed. That's one of them.
Wow.
Mutated over a couple of days, really. It went long and thin, and yeah. And we also had the large Cassegrain telescope. We haven't had a lot of images out of it, but these were just a few base prime focus moon images, and that was on the Exos 2 as well. So was a little bit overweighted, but as we said, it worked. So yep, they were
an 8-inch with an 8 Cassegrain, is that right? 8-inch?
10-inch.
10.
Yeah, so it's
Okay.
just
Yeah,
10-inch.
I would agree with you. It's a bit over.
10-inch at prime focus.
Yeah.
And then if we move on to the 31st, the prominence changed shape on there. So I'll just come over to the 31st. Might even be day after that.
Got a couple of files.
Right. Yeah, there's always plenty of files in there. I'm sure it was in here. Yeah, there we go. So it changed shape.
Look at that.
Oh, that's nice.
Quite dramatically.
Look
So
at
again,
the
still running in quite
blobs. It
close
looks
to the
like
sun.
it's falling back in on itself or something.
Yeah.
You know?
You can see a lot of plasma being pulled up and dropping back down. So not the best conditions from this side. And we did have a filament on there. These are quite unusual at the moment, with the sun being fairly quiet. And they really take off filaments, all different shapes and sizes. So it's quite nice to see a few of those larger ones. So they can look very similar to a caterpillar. It's the easiest way of putting it. So let me just go back to...
Is it also true that we've already passed through solar minimum and we're,
Well,
you know?
at the moment, there's really 3 active areas spanning across the sun. So while we're quieter in some, just stop.
I think we.
Areas, really, it's not overly quiet. It's fairly good at the moment.
I think, Gary, we've lost your video.
Not again.
We can see your profile picture. It's very nice, you know.
Yeah, I can see the profile picture.
Yeah, that's nice.
It's just crashed again. Let me come out of this and I'll rejoin you in a minute if you can still hear me.
That's fine.
Yep.
That's fine. Take care, Gary. Maybe we'll see you later in the program. That's great.
Yeah, thanks.
All right. So, Jerry, we were talking about what's up on the forum today, and you brought up Mike Leemhuis, and
yeah, Mike Leemhuis
contributed a couple of shots. What is Mike shooting on? Which
he's got an Exos 2 mount. I'm not sure what his. I have to see what it says in detail. Let me share my desktop, and we can look. And he shared an image he took last night of Comet NEOWISE with next to M53. And I've got it up here along with the Carte de Seal depiction of it. I've rotated it around to kind of match what he did. So you can see...
That's M53 down there at the bottom?
Right here is M53. And I'm not sure how good that shows up on it. Maybe I can zoom up on it a little bit. Let me try that.
Look at that deep violet color of the comet.
Yeah, that's really wild. He asked about that color. He's not sure why it came out that way, but that's quite a large field of view.
Mike's saying it's a QHY 163C camera.
Yeah, that's the same camera we have on the MSRO. Is he online with us? Is
Yeah.
he on the? Okay, cool. So I basically so basically I plotted it on the approximate time last night, and just to verify what it looked like in the sky. This image is rotated.
Is that that star map program that you have, is that fairly accurate as far as which way the tail is going and everything too? Or
No, I don't think so. I think this is just a graphic depiction. I don't
Mike
know
said
that it.
1.5 degrees field of view.
Okay.
Mm-hmm.
That's
And Dusty wants to know if he shot it with his 60mm guide scope. Mike Overacker, this is Comet NEOWISE near M53. So this is a very cool shot. He's got more than one image, is that right?
Yeah, so the second one, let me bring that one up.
So this one's obviously guided on the stars.
All right, he actually, I'm going to zoom out a little bit on this.
I see. This one's guided on the Comet.
On the Comet, right. So the colors looks a little better to me.
And you can see
not quite as pink.
You can see the tail. It is kind of going off to the right there. Mm-hmm.
And you can still see the cluster there. It's just smeared the way the stars are stretched out that direction.
Mm-hmm. Did Mike give exposure data on this?
Let me look. I don't think so. Maybe he can chime in and tell us a little bit about. Well, he says there's 21 60-second exposures.
Okay.
And so they're 1 minute each. I'd be interested to see what an individual exposure looked like, because then the comet, of course, the comet's probably not that bright in that one exposure, so you may not be able to see it very well compared to the cluster.
Yeah.
And yep.
Beautiful.
So that's kind of cool. We had mentioned this yesterday during the episode that it was going to be passing near a cluster.
M13.
But this is, yeah, I'm not sure when it would pass through M13.
According to Gary, it was last night.
Yeah, this is M53 though.
Right.
So I don't know. I don't know how close M53 is to M13.
Yeah.
You know, maybe they're near each other.
Yeah.
I'd have to look on the chart to see.
Right.
So that's that. I don't know that we discussed a whole lot about what we're going to talk about today.
Well, we always have things to talk about, Jerry. So,
yeah, I'm sure we can find something. We're going to give something away today, aren't we? Are we going to give something away or not? Okay.
Of course. We gave away a big prize yesterday, which was an eyepiece. But if you got a question to challenge them with, that's great. We also still have subjects to cover in your future of amateur astronomy. You know, so if you want to talk about another section of that, that's cool.
Let me see.
Mike Leemhuis says he loves photographing comets. He says they don't happen that often with tails. Bill Black says it looks like M13 was about a week or so ago.
Oh, okay.
Yeah, okay.
That's what I was wondering about.
Yeah. Hey, it was still a globular cluster, right?
Mm-hmm.
That's right. Bergman Scooter said a while ago while we were showing the NASA Mars 2020 rover, he says they should have sent a PMC-8 to run some of the equipment.
Yeah.
And Bergman Scooter said maybe they did. Who knows? That's right.
That's for us to know and you to find out, I guess.
That's right. Yeah, that's right. Yeah, there's Explore Scientific, and then there's a subsidiary called, some of you might have heard of it. It's called NASA. You know. Yeah.
That's right.
Oh.
No, but I thought it was interesting seeing all those really fine instruments and detailed, really precision machining with the robot arm underneath the lander.
Oh yeah.
It seems odd. I mean, not odd, but the rover, I should say. It seems that
well, you notice
the dust is
putting the samples up underneath, to
yeah. I don't know how much static.
Testing, I'm sure it
I don't know how much static electricity gets built up on that,
Oh, man.
and it attracts dust,
Oh yeah.
So I'd just be curious to see how that works. They've got a lot of experience running rovers on the planet. There, they've got 15 years of experience, so I'm sure they take all that into account.
Here's a question for you. Okay, Michael Whitaker says we didn't answer this question. So Michael Whitaker's question is, do you think that augmented reality will have a future in astronomy and or astrophotography? I happen to think it will. Because there's, you can take so much information of, layering that you can do in augmented reality, even maybe like some holographic type of things, with stars and star distances and stuff. It would be cool to have a visualization where you're maybe looking inside of an eyepiece where there's AR going on, and or wearing goggles and you're immersed in kind of a planetarium kind of view, but somehow a real live image is coming in as well from your telescope. That would be very cool.
Yeah, I could foresee something having like a virtual eyepiece where you have these augmented reality glasses on and it projects the eyepiece view on your, and then you have overlays with star images like a catalog overlay.
Yeah.
Like you see with astrometry.net, where you have the overlays to show you what objects are there.
Sure.
And it could just not just be a small field of view, but a very wide field of view also you could have.
Mm-hmm. I think the dogs started barking because
they
got Gary back up on the screen.
Yeah, they did. Is he? Hey, Gary. It looks like we all were color coordinated today. We used our dark
that's
sky,
right. We're all
dark
wearing
sky
the
shirts.
Our Scientific black shirt today.
That's right.
So that's right.
Mm-hmm.
It was very cool. But okay, Jerry. So what's going to be your question? Because I know what the prize is going to be. We're going to do a red flashlight and a planisphere combination. So.
Okay, so I've got a question that's not. It's just a general astronomy question. What star recently, in the last few months, was talked about that astronomers were very interested in it, and they were wondering if it was going to explode? You remember that, Scott?
Sure do. See how fast we get answers here.
Yeah. Mm-hmm.
There shouldn't be too much Google searching with this one.
Jeff Wise won. It's Beetlejuice. Yeah.
Beetlejuice, that's right.
Yeah. And who else? Dusty Haskins. It was a tie, really, between Dusty and Jeff, because those both popped in at the same time. So we'll give them We'll give prizes to both of them.
Oh, that's nice.
And so
it's a flashlight,
guys. Flashlight and a planisphere. Yep.
Okay, here's the flashlight.
Yeah.
Can you see that?
Mm-hmm.
And
you
can
somebody over the head with that.
Like a see it blanks me out when it hits me in the face.
I watched a Timothy Leary video one time, where, it kind of looked like that. It was pretty psychedelic. So as Timothy Leary was, so anyhow, well, that's great. Any other topics that you'd like to cover today, Jerry?
Let me see. Give me a second. I'll look at the forum and see if there's anything else we're talking about today.
Mm-hmm. But I like the idea of AR, I don't know if I would get a headache from it, or, if I would just be so immersed in it that I would just get addicted, I'm afraid I would get addicted and want to spend hours in there and maybe starve to death.
Oh, yeah.
Because I wouldn't want to do anything else. Mr. Thump 30 says maybe Beetlejuice already exploded.
Could be.
Nico said Facebook took too long to post the comment in the video. He's laughing. Laughing hysterically. That's right.
All right, so quickly,
Go ahead.
I just have one thing that somebody asked. It was from manager. I don't have his name or her name, but they thought they had the right cord for the iXOS 100 to connect up to the computer.
Yeah.
But it didn't seem to work. So we may have discussed this once before a while ago, but basically it uses the same standard USB to mini USB connector, type B, and but there's two types of cables out there. One you typically get with your phone, and it's interesting that they do this. This is a charging only cable, so it only provides 5 volts to charge your phone from a standard USB port. So you wonder how much money do they save by leaving out the 2 or 3 wires out of the cable that it would take. You need a full cable of which includes the communications wiring, not just the charging, the 5 volt wiring in the cable. So if you have cables laying around, it could just be a charging cable and it may not work for you if you try to connect it up the iXOS 100 to your computer. So it's important to get one that's got the full cable. Now, I imagine depending on what phone you get, you'll get a nicer cable, or maybe not so nice a cable. I don't know.
Right.
So that's what you'll run into if you don't have the right cable. You won't be able to connect to the iXOS 100. And you may think you didn't switch the connection correctly or something, or you may think, oh, it didn't work. So
right,
that you can run into that.
Right. Gary, Jeff Wise says your photos were excellent, and Chuck Lewis says for Gary, should we assume those spots are from cycle 25? Would you know?
Yeah, there's very mixed views on the spots at the moment and how they're displaying themselves. All of the active areas at the moment are on the top of the sun running across. So there's very little running across the bottom of the sun, as there was a few weeks back. So the sun still goes through its transformation. And while it's transforming, you will get sunspots all over, really, in different locations and sporadically appearing. They don't always rotate on from the limb and form out of our sight. We've had quite a few over the last 6 months that have been forming halfway through a rotation of the disk. So when you're looking, they start to appear somewhere around halfway, or maybe even 2/3 of the way across the sun. But we're still not really at that stage where the sun's active enough to get a full rotation of the sunspot. They seem to be disappearing very quickly. There was a small one I imaged last week, last Thursday or Friday, and I was hoping to get back on there. It had a nice little light bridge on it. It was quite small, but next time we go back on there, it's gone. So, but thanks for the comments on the images.
Yeah, it's great. It's great. Jerry Wolfgang says, I've purchased 2 similar USB cables. The only one that works best with the DSLR. There's only one that works best with the DSLR, and the other one only works only with the IXS 100.
That's
yeah,
weird.
That's strange.
Yeah, that is strange.
And Jeff Wise says cables don't last forever either. So. But,
that's right.
So some of the cables at the moment are very, very poor. Even coming out with quite expensive equipment, they're very poor. We're noticing that they degrade over the winter with the cold weather. The outer casing, sheathing just splits and peels, and
it wasn't really
there are
outdoor use, was it?
Yeah, some of the cables. I mean, to be honest, a lot of stuff I just purchased other cables from Amazon or eBay or somewhere, and those seem to last a lot longer than what's being supplied with a lot of the equipment.
Mm-hmm. Right. With regard to augmented reality, Bill Black comments makes me think of the holographic star maps in Star Wars.
Mm-hmm.
I guess that's a possibility.
Well, I always liked, when Luke first pulled out the binoculars that had the overlay and the rangefinder and stuff. That was cool to me. That display.
Yeah, James Bond always had like some really cool binoculars too.
We need to develop some augmented reality binoculars like that with the rangefinder display and other things. With the
can all be done with the little.
Could you imagine having plate solving built into the binoculars? When you point it up at the sky, it plate solves, and then it overlays the star map on top and that type of stuff.
Oh, that'd be very cool. Very cool.
Let's keep that in our back pocket.
A little desktop, like suitcase with you, processing all that data.
Yeah.
Mm-hmm. Do we have any other comments here? Wolfgang says they were from Hama brand, 2 meters long. I needed them because I have my PC inside and my mount at my balcony. So I'm sure the Hama brand. People
run a powered USB hub local to their machine, and then they run a long 30-meter or 10-meter, I should say, powered cable from their inside their house to the outside. I did that in the past before I went. That's how I would somewhat remotely operate and there's quite a few people that do that today with one USB cable running into their computer in their house from the telescope.
Right. Well, oh my goodness. Richard Gray says he's running a 65-foot powered cable. That must be
yeah.
That's a monster. Jeez. That's great.
There's another way to run it if you can convert it to Ethernet. You can convert the USB to Ethernet and run a 100-meter Ethernet wire.
Yeah.
That way, that gets you longer distance.
Right.
Well, I think the problem comes with video, with actually capturing the pictures and the cameras. Most of the USB 2 cameras are quite stable. But the USB 3 cameras can be a little bit like a box of frogs once you start extending the cables. Some connect and some don't. And
I love that. A
box of frogs.
I love that.
Yeah.
Maybe that's a common thing to say in the UK. I don't know.
Yeah,
I'm going to remember that one.
As stable as a box of frogs.
I love that.
So,
that's awesome.
Yeah.
But yeah, under USB 3, there's all sorts of problems. And most of the deep sky cameras, we're saying, even though they've got USB 3, is to actually use the USB 2 socket inside that. So the socket contains two sockets in a sense. And under USB 2, most of them are fairly stable. You can run them up to 30 to 50 feet. But the USB 3, really an absolute maximum is probably 5 meters. And there's very few powered hubs that work very well for doing actual live video capture. So this is where the advent of the more local computers, there's lots of different devices coming out on the market.
Sure.
ASI, Air Pros, and Prima Luce Lab. Their Eagle units and all sorts of things are actually mounted by your telescope now, and this solves a lot of the problems of the long leads. But you still got the control issue. So whether you want to run USB to control the mount, or whether you're going to run wireless and maybe take the problem with some instability on that.
Right. Yeah. It's hard to win. You know, you got to come up with reliable, high-speed. You're going to do some of this stuff. Which brings me to a couple of points, Gary. One of them is that I'm almost done setting up my system behind me, okay? And
Yep.
I think I mentioned to you earlier, I'm not sure, but I have a Lunt H-alpha system for it. And
Yes.
what I'd like to do is get it all dialed in and aim it at the sun and have you control the scope and
Excellent.
show me the ropes, you know, so that would
Yeah,
be kind of cool.
that sounds good.
Yeah.
That sounds like good fun.
Yeah, and then we talked about we had our virtual star party on Tuesday. We're going to do it again here in the States next Tuesday night.
Yeah.
And we got a couple of people joining in on with us, but we have people in the UK. We got certainly at least one guy in Germany that wants to be part of it, and so with the time difference. I kind of determined that we would probably start at about 4 or 5 p.m. Here central in Arkansas, and it would be around 11 o'clock or maybe 12 o'clock where you guys are, and by that time at least it would be dark, and it's
pretty dark out there now. I just wandered out when the Skype connection dropped, and I mean I can see all of the planets up and. Yeah, it's just a little tiny bit blue on the horizon over to the north. So you can certainly get away with imaging high up or over to the south.
Right. Well, I think we have enough people to put together one of these virtual star parties in Europe, and or at least for that whole time zone. You know, if you're in the southern hemisphere, great.
Yeah.
Chime in, and if you're watching, and let us know who you are. We will be connecting on Zoom, and you need a good internet connection to do it. But anything can happen on these kinds of shows. You know, you can have people drop out, or or it could rain on somebody like it did on Richard, poor guy.
Right.
But he's going to be, he'll be coming back on Tuesday. Everybody that was on the show will come back at the first part of it to show the results, of which I think David Ng and Jerry Hubble were the only ones that got data. But Alberto Levy will be back with us, and Richard Grace, and then we've got a couple of others that will be joining in as well. So Jenny Del Shelley says, I like the idea of having separate U.S. and international editions of the virtual star parties. Eventually, when we get it all coordinated, we will have a simultaneous daytime, nighttime star party. So that's the goal. We'll do 24 hours of astronomy, and I'll take a bunch of caffeine to stay awake.
Yeah, right.
That was done on solar a few years back, where it was going all around the world. Started in Australia and
that would be cool, wouldn't it?
Went right the way around the world on that would have been on the solstice day.
Yeah. Oh wow. Wow.
Yeah.
So maybe we do that. That would be very cool.
Yeah.
But anyways, that's right. Astor Beard saying, Richard Grace is saying Star Party Marathon. I know he's up for it. That's for sure. Oh.
Cool.
Gentlemen, thank you for joining us here, and our wonderful audience that we love so dear. Thank you for spending part of your valued afternoon here this Friday afternoon. And we hope you have clear skies this weekend. The moon's starting to get less and less. And if you guys have been watching Jupiter and Saturn, you've also been watching it kind of separate in the sky. So that's kind of cool. It really gives you, seeing stuff like that lets you feel the dance of the planets, for sure. And anyways, we got an exciting week planned next week. We've got some special speakers that are coming on board. So I will be sending out emails about that and announcing it here on social media, Facebook, YouTube, etc. So you guys keep looking up, and thanks a lot, and keep looking up. Good night.
Thanks.